All right. Hi, everyone. Sorry could not be there in person. Looks like a nice vibe in the room. So yeah, I'm going to be talking about grokking, which is a surprising thing that happens in neural networks that was recently discovered and I think is relevant to alignment. I probably talked to a fair number of you guys about this already, and some of it is going to be similar to what I already said, but I think it's cool and I added some new stuff too. Okay. This is work I did with Laro at the Kruger lab. And yeah, Laro also gets, if you think it's cool, it's Laro. Okay. So yeah, first I'm gonna talk about what grokking is and make you be surprised by it, hopefully. Then I'm going to pitch you on possible theory of what's going on by talking about a related phenomenon. And then I'm gonna talk about why I think this is relevant to AI safety. I think this is kind of a surprising order, but it's because I think that the grokking stuff is really cool on its own, even outside of the context of AI safety. Okay, so here's the task. We are training a neural network, in this case, a transformer, though you can also use simpler architectures on modular division. So basically we pass it A divided by B equals, where those are like encoded. So they're actually long vectors where there's like a 1 in the corresponding place. And we basically have this 97 by 97 modular division table. So we're doing modular division up to 97 by 97. And you take half of the data as your training data, and then the other half as your test data. So that's what I'm going to be talking about when I say train and test data. We're going to not train on part of the division table, and we're going to use this to evaluate how it's doing at the actual task we care about. Here we're going to train with cross entropy loss, which is standard, and usually stochastic gradient descent, though that's not too important. Okay, so when we do this, what happens? Well, very quickly, we achieve perfect performance on our training set. That is, we get to perfect accuracy on the training set. That's this red line here. But we do terribly, basically at chance, on our test set. So the bit of the multiplication of the division table we withheld is we're just outputting random nonsense. And at this point, usually you need to change something, and you stop training your model, and you say, okay, maybe I need to like have really heavy regularization, or maybe 50% of the table is just not enough. But some people decided, what if we just like kept training it? Or actually, the lore is that they like just forgot to turn it off, and this is what happened. So you can see that after a while, the test accuracy sort of looks like it goes up suddenly, and this is pretty weird. I think it's worth noting that the x-axis is log scale, which makes this effect look like way more dramatic than it is. But still, pretty weird. You could plausibly have stopped training way too soon. Okay, so yeah, our goal is going to be to sort of understand why this might be happening, not really in terms of what's going on when you like look into the model, but more like what are the training pressures that make this sort of behavior happen, and how do we think about this behavior and like when to expect it in other situations. So yeah, basic way of thinking about this is that at the beginning here, you have memorization, and then eventually it seems like you get actual comprehension. I'm not going to really talk too much about this loss curve. Let's go on and emphasize the weirdness. So yeah, one thing that's weird here is like, because you're having perfect training performance using this like memorization, poorly generalizing thing, it seems like you should be able to get to zero loss that way. So you should just be able to say, okay, let me just become more and more and more confident in my memorization. And this should, this is like a valid approach to get to a zero loss global minimum, but it's not the approach that we go with or the model goes with. And so it seems like there's this like extra pressure happening towards something that we like, which is this like better generalizing situation. To quickly talk about some theories that have been floated that I don't really agree with. There's like a random walk theory, which is basically saying that grokking happens because we just randomly stumble into this like especially good minimum, and then once we're in there, we don't escape. I I don't think this is right, mostly because that's just like not what the training curves look like to me. They look much more consistent over different runs and things like that. There was also a recent paper on the slingshot mechanism, which was sort of framing Grokking as a property of adaptive optimizers, like different from SGD. I don't think this is like a good way of thinking about it, mostly because, Grokking happens with SGD. So yeah. Okay, now I'm going to move on to talking about a related phenomenon and some explanations that have been around for why this one happens, and then argue that maybe this is what's happening in Grokking. Okay, so this is called Epoch-Wise double descent. The best thing to look at here is that like maroon large model curve. And the thing to notice is this is test error. So this is not training error, which smoothly goes down the whole time. But here we see that until around, I don't know, 50 epochs or something, we're like going down as expected, but then we start going up for a bit. And then we see a second descent where we come down again. Okay, so that's double descent. And the reason it's epoch-wise is because our x-axis is number of training steps. Whereas you can also show similar, where your x-axis is like the size of the model. And every point is evaluating a new model, which is much harder to run. But yeah. Okay, so an explanation that was floated for this is that this double descent happens because the model learns different features at different speeds. This creates like two separate bias variance trade-offs. So that's this, these two like dotted lines on the right side. They both have these like dips where it's down and then back up. And this like down and back up dip is like much more normal in machine learning, and we're sort of comfortable with it. So if you put two of these down and then ups together, you get this like green line, which has this double descent. So they were basically saying what happens is different parts of your model learn things at different speeds. And when these don't sync up and you learn certain features way before you learn other features, this causes like weird looking graphs. Here's some evidence for that happening. This is from a separate paper. This looks at the exact same setup as here, this red one, but it takes the data set that they were using to train on, and it uses PCA to only keep a certain number of components. So basically doing dimensionality reduction on the training data set. And it turns out when you do this, you totally remove the second descent behavior and you just see one descent. And they use this as an argument that it is the like slow learning features which come from these things not captured by the first 50 principal components. There's also other evidence, like if you vary the speed at different parts of your model, you can totally stop this from happening. Okay, so theory with respect to Grokking is basically it's the same thing going on where you have fast features and then slow features. But because of our data set being sort of weird and not like a natural data set, but instead an algorithmic data set, our fast features are memorization, which means they don't generalize at all. So what was going on here is that fast features generalize a bit, but just like not great. So it might be things like you're doing classification and like dogs are in grassy fields way more often. So you just like use the amount of green. This isn't a great approach, but it definitely correlates with generalization and will still make you do a bit better. In the case of Grokking, when you're trying to train on an algorithmic data set, these sorts of tricks just don't work. You have to actually learn the generating function. So yeah, this is basically showing that when you train on random data instead of the actual modular division data, you get the exact same training curves. There's more like sort of dynamic stuff that I can point to. But basically, yeah, fast features seem to just be the same sort of fast features as you would get in any sort of random data set like this. And then in Grokking, our slow features actually are useful, and models which are trained on the real data set can in fact get lower train loss. This is something I'm exploring more, and I think there are like cooler graphs for this, but here's a simple graph which shows that the real data does get lower loss than using random data. There's also some evidence that varying the step sizes, so encouraging parts of your model which typically learn slower to learn faster, alleviates grokking, which is actually something they showed here, which is that if they slowed down the later layers, which typically learn things faster, they could stop double descent from happening. Yeah, okay, so that's most of the theory. I only have like 90 seconds, so I'm going to briefly talk about the alignment relevance. Basically, I think that generalization behavior is like one of the central questions to making sure that AI is developed safely, because ultimately we're going to be taking this thing which was trained in a certain environment and we're going to be bringing it somewhere else. And this is just a scary thing when you have a very powerful agent, and it seems really important to understand and know what to expect when we do this sort of distributional shift thing. Yeah, this sort of is broadly under the banner of inductive biases. So trying to understand which solutions are favored by training setups, even if they perform equivalently on the training data. This includes both like explicit biases, like using regularization, and also implicit biases, like gradient descent preferring some solutions over others. I also think this has a pretty nice intersection with what academia is interested in right now, which I think is always good. So yeah, happy to take questions now. Thank you for all the great CERI things that have happened and for interesting presentations.
Yeah, that's everyone clapping for you, though you probably couldn't hear it through the microphone. We now have around 5 minutes for questions. One from the front here.
When you learned this about grokking, what did you change in your own life to learn things better?
I don't know. I think there is definitely an overlap between how it feels like to do math or something, where you just have this period of just staring at things, and then maybe you can get by using tricks, but then at some point you get it. Yeah.
Any other questions? Everyone's grokking, apparently.
I should have called it grokking.
I have a question from Som.
Okay, so what do you think are like good next steps or next questions to ask? I think you sort of peppered them through the talk, but if you could just like collect them in one place, say.
Yeah. So it does seem like these like slow features are useful, but I think getting a better understanding for why they're needed and parsing out what the different inductive biases are. So like there's oftentimes these models are trained using weight decay. Seems like weight decay probably plays a role. Sometimes though, you don't need to use weight decay and it still happens. So just trying to understand like what is the source of this inductive bias, even once we say, okay, we're pretty confident that this thing is preferred. What do we mean by preferred? Do we mean that we've accidentally regularized for it through something obvious, or that there's like something subtler with gradient descent happening here? There's also a question of why the model is able to learn these slow features. So there are certain cases where there are slow features which are left to learn, but something called gradient starvation happens, and the gradients just get really, really small because your loss is like really low. And when that happens, often the model is like unable to get to this like better state, but it seems like here we don't have a problem with that. So I think trying to understand what's going on with the gradients and how they're actually persisting through the model would also be good.
Any more questions? Okay. Yeah, I guess like I've got another question. So the Grokking example that you use, like the data set is like division. In what sort of data sets does Grokking also happen? Has this been like investigated further? And for what does it not happen?
Yeah, so I mean, if you believe me about the slow and fast features thing, you need the fast features to not help with generalization. I think this like is unlikely to happen in most natural data sets. So I wouldn't really expect it in something like image classification, though there could be like carefully curated data sets where the fast features do happen to not generalize well. But I think in like normal settings, I wouldn't expect that to happen. It has been shown in a wide range of algorithmic tasks though. Yeah, I think this basically makes sense. I mean, if there's like a really good slow feature to learn, that ends up being preferred. And then you have a model big enough such that it can easily memorize, then you'll see this happen. So certainly like modular addition does this. Neil Nanda has like, I think like 4 other tasks or something where he showed this happen. They're mostly like kind of cutesy algorithmic tasks. And yeah, I think it would be interesting to try to make it happen with an image data set, but it would have to be like pretty toy.
Thanks. How much time do we have left? Okay, 1 minute left. Any more questions? Okay, Pranav.
Hi, so I just noticed when Hannah pointed it out that you're using division while like the original Grokking thing was addition. Any particular reason for that choice?
No, the original Grokking thing was not just addition, and like the main graph that I showed with the fade in is division, and that's directly from the paper.
Oh, I thought it was addition. Thanks.
No, yeah, it's both. They show it for like 4 or 5 different operations. Actually, I think more than that, because they also show it for like x squared plus y squared mod 5 or something.